All right, good morning, everybody. So in the last lecture, we were talking about the relationship between classes. And in particular, we were talking about aggregation. And so we had this little example here, the person class. Now, this class is a little bit different than the ones we've implemented thus far in the course. Its fields are of reference type. So here we got a class that has a name field called string. Has a string field called name and a date field called birth date. Right, so these are now references to objects as opposed to being primitive values. If you implement a class that has reference fields in it and you just pretend that the fields are of primitive type, you end up with an association or an aggregation, one of the two. Right, and so if you just do what you've been taught to do so far, right, so in your constructor that takes in a name and a birth date, you just assign name to this dot name and you assign birth date to this dot birth date. In get name, you return the name, and in get birth date, you just return the birth date directly. You end up with this is exactly what you would see if you're implementing an aggregation or an association. Right? So if you pretend that your reference fields are just primitive types and treat them as such, you end up with an association or aggregation. In this particular case, it's an aggregation. I'll explain why in just a second. Right? The key here is that there's no new objects being made anywhere. Right, so there's no, in the code here, there's no new string being made when the constructor assigns the name. There's no new birth date being created when the constructor assigns the birth date. When the method returns the name, it doesn't make a copy of the name and then return the name. And when the method returns the birth date, it doesn't make a copy of the birth date or it returns the birth date. Right, so no new objects are being made. Right, and essentially what that means is that both the person or both the user that created the person object in the first place and the person object itself, neither one of those two entities actually ends up owning the string that represents the name or the date that represents the birth date. Right, so if someone has a string S and a date D and they make a person using that string and date, you end up with the following picture. There's your one string object that represents the name. There's your one date object that represents the birth date. The caller has a reference to the name, right? And the person has a reference to the name, right? They have references to the same string object, right? Neither the client or the caller or the person object has any ownership over that string object. I guess you could also say they have shared ownership over that object. Right. Similarly, with the date object, right, there's your birth date object. The caller has a reference to that date, and the person object has a reference to that date. Right. And what that means is that either the caller or the person object can change the date, and that will cause the other, either the caller or the person object to see the change to date. Right. So here, the caller is using their reference D to change their date to 1995, November and 3rd, right? So they changed the birth date, or they changed their date object to November 3rd, 1995. When you ask the person object, what is your birth date, right? The person object now says, well, my birth date is now November 3rd, 1995, right? It's no longer March 26, 1990, which you might think is unusual, and it might be depending on what you're trying to, what your person class is trying to implement. But this is the consequence of using an aggregation in this case. Okay, so because the date instance is shared by the caller and the person, right? The client or the caller can modify the date using D, and the person instance sees the modified birth date. The opposite is true, right? So the person object can now change the birth date if it wanted to, or if it had some reason to do so, right? And now the caller would see a modified date object as well. Right. Now notice that the string object, it's shared by both the caller and the person, but strings are immutable. So neither the caller nor the string can neither the caller nor the person object can actually change that string. Right. So that name is forever, whatever the name happened to be set when the person object was created. Right. And so you'll often see that if you're one of the recommendations that's made is that you should try to use immutable objects like string to build your classes. Okay. it lets you, the reason for doing so, the reason that advice is often given is because you can freely share immutable objects and you never worry that their state will change, right? So in this particular case, we never have to worry that the string that represents the name ever changes. Neither the caller or the person object can actually change that string. Right, this makes your code easier to write. It makes it easier to debug. It makes it easier to maintain. But of course, you can't always use immutable objects. Okay, so the person object, the person class in this case is an aggregation because the relationship between the person and the date is one way. Right, the person has a reference to the date, right, but the date does not have a reference to the person, right? And there's no way for you to go into the date class and add a reference to the person. Right, so because the relationship is strictly one way, this is an aggregation relationship rather than an association. Right, association is allowed to be two-way. In this case, it's impossible to make a two-way relationship. So a person is an aggregation of one date. Right, in the UML class diagram, if you're going to illustrate an aggregation, it looks like an association, except you include a an open diamond on the whole object. Right. So you'll often see the term whole and part object. The whole object in this case is the person, right? It's the thing that's made up of the parts, right? So it's made up of a date and a string. So the open diamond goes on the whole object. There's no symbol on the part object. Right? The open diamond is significant. The closed diamond means something else. Right? Similarly, a person is an aggregation of one string object. Okay, here's another example of a another aggregation example. And so in this example here, I'll show you the running program in a second. You've got a ball that's bouncing around inside of a box, right? Inside that, inside the screen, inside the window there, right? That ball is just following the equations of projectile motion that you learned in your first year physics course, right? So the position of the ball at time I+1 is equal to the position of the ball at time I plus the velocity of the ball at time I, right? Times the difference in time plus 1/2 gt squared, right? Again, where t is the difference in time between step I+1 and step I. Okay, so if you actually look at the code in this example, you'll see that this thing projectile has a point that represents its position, right? It has a vector that represents its velocity, right? And the projectile is using aggregation in this case, right? So if you look at the code for this, it's got a point representing the position. It's got a vector representing its velocity. The no argument constructor has to set the position and velocity to something, so it just sets them both to 0, 0. The method that returns the position simply returns the field this.position. That should be this.pos. There's some copy and paste errors on these slides. Right. Similarly, the method that returns the velocity returns this.vel. Right. It just simply returns the reference that it has. Right. It returns. It directly returns its field. That and that. Right. Set position. So this is the method that takes in a new point that represents the new position of the projectile. Simply assigns its field to be equal to p. Right, now remember what that does, right? That doesn't make a new point object, right? It says that the position of the projectile is the same object as whatever got passed in. Right? And similarly, set velocity does the same thing, right? It doesn't make a copy of the incoming vector, right? It simply says that this.vel is the same object as the object that was passed to the method. Right? And finally, move. Move is the thing that implements that equation that I showed you earlier. Right, and it uses the point and velocity classes to implement that. Right, this isn't actually important how this works. Right, move simply moves the ball to the next position, given some time step dt. But again, notice that. Oops, sorry. Right, again, notice that when it changes the position, right, it doesn't make a new point object here. Right, it simply uses the current position and modifies it somehow. Right, similarly with the velocity. Okay, so implementing that class turns out it's pretty easy, right? The methods are all basically one line or a few lines with for move. All of our references to the existing objects are provided by the caller, right? So the position of the projectile and the velocity of the projectile, those are all provided or can be provided by the caller. Right. Are the accessor methods? They don't make new point or vector objects. They simply return the fields representing the position and the velocity. Right. And similarly, the mutator methods, so the ones that change the position and velocity of the projectile, they don't make new objects. They simply reassign their fields to whatever the caller passed in. Right. And so the fields belonging to the projectile are actually aliases for existing objects. Right. They're just different names for objects that are passed in by the caller. So for example, if someone makes a point and a vector, and they make a new projectile, right? They call set position and set velocity. That should be VEL, right? So they call the two methods to set position and velocity, right? All that's happening is that there's one point object, right, representing the position. There's one vector object representing the velocity. Right? The caller has a reference to that point, right? The caller has a reference to that vector. The projectile has a reference to the same point and the same vector. Right? So the projectile doesn't have its own independent point or vector object. Right? And what does that mean? It means that should be VEL again, right? That means if you ask the projectile, what is your position, and you compare it to the variable POS, right? And you ask, are they the same object? The answer is yes. Right? So is that the same as that, right? Sorry, projectile, yes. So is the ball's position, right? Is that reference equal to that reference? The answer is yes, right? They both have the same value. Now, if the caller changes that point object POS to a new point, right? You don't even have to ask the ball for its new position, right? For its position. You can simply use the variable that was returned from before, right? And now the projectile says, hey, my position is minus 99 and minus 22, right? So the position of the ball has changed, even though you never asked the ball to change its position. And you didn't even ask the ball for its new position, right? We're using the old variable that was created back here. And it now appears that the ball's position has changed. Right? And so basically what happens in this code is that whoever made the projectile can move that ball wherever they want it, that projectile wherever they want to, right? They can set its velocity to whatever they want to. And they never have to actually ask the projectile object itself to change either its position or its velocity. If that seems weird to you, it's not. It's just the consequence of how things are implemented. Right. So here's what happens when the caller uses their variable POS to change its position, right? So the object at address 250 is our point object, right? Change its position to minus 99 and minus 22, right? Notice the projectile has a reference to that object. So whenever you change that object, projectile object also sees that change. Right. So the caller can get a reference. So this is true in general. If a caller ever gets a reference to one of your internal fields that belongs to an object, all right, the caller can now change the state of that field without asking the object itself. Right. So in this case here, the caller can change both the position and the velocity of the ball without ever asking the ball. Right. This is not a flaw. Right. So many programs, when they see this for the first time, say, "Hey, well, that's really weird. We shouldn't let that happen." Right. It's not weird. Well, it might be weird, but there's nothing actually broken here. Right. It's just the way that aggregation works. The same is true in association. Right. The exact same thing would happen. Right. And so this is simply a consequence of your design. Right. If you choose to implement an aggregation, then this is the sort of thing that might happen. Oh, sorry. Okay. So in this, in the bouncing ball program, right, the one that bounces around all the time, If you're implementing the projectile as an aggregation, right, then if you're moving the ball around from point to point from one time step to the next time step, right, all you're doing is updating that one point object every time, right, because the one point represents the position of that ball. So that program ought to really only need one point object, maybe a few others, depending on how you're making the point object and how you're passing it to the ball. Right, but it should only ever need one or a small number of points and vectors. Okay, so the next relationship between classes is this thing called composition. Okay, so what does composition mean? So composition means the same thing as association and aggregation, right? So if X is composed of a Y, right, that means X has a field of type Y. Right, that's exactly what association and aggregation mean, right? However, composition also means X owns the Y object, right? So not only does X have a reference to a Y object, but it actually wants to own that object itself. And by ownership, I mean sole or exclusive ownership. Okay. So in other words, that X object always has exclusive access to its Y object. Whoops, sorry. Okay, so what does that mean, right? So that means if you're trying to implement a composition, right, you have to make sure that you never release a reference to that internal Y object, right? And releasing that reference can happen very easily, right? It's very easy. It's very easy to accidentally reveal a reference to an internal object, right? And so where might this happen? It can happen in the constructors of the class. Right? It can happen in any method that tries to return something about that Y object, right? And it can happen anywhere where you have a method that tries to set that Y object. Right? And so if you can't share a reference or you can't hand out a reference to that internal object, right? Whenever you need to, for example, return a reference to that Y object, you have to make a copy of that object, right? So everywhere you see new Y object, right? All of those new Y objects are copies, right? And those things are called defensive copies, right? Defensive because you can't afford to release a reference to the actual Y object itself. Okay, so in your no argument constructor, this isn't really an issue, right? The no argument constructor typically has to assign a value to all of its fields, right? So if X has a Y, you're going to write this Y equals new something, right? Make your Y object and away you go. That's not really a defensive copy. It's just the way the no argument constructor has to work. Okay, so what about a constructor, though, that takes in a Y object from the caller, right? So like our projectile class that takes in both a point and a vector, right? So if the X object needs exclusive access to that Y object, right, it can't simply write this dot Y equals Y, right? Because that doesn't have it does not have exclusive access, right? The caller has a reference to that Y object, right? Your X object has a reference to the same Y object, right? That's not going to work in composition. You have to make a copy. Right? So if you're implementing a composition, the first thing you're going to do is you're going to copy anything that needs to be copied. Right? So in this case, X needs to make a copy of that Y. Right? So here I'm using a copy constructor to do that. Right? The problem in Java is that not all classes have a copy constructor. And it's not always possible or obvious how you make a copy of an object. Right? So if whoever made Y decided not to include a copy constructor, you may have a problem. This is arguably one of the flaws of the Java language. They didn't actually put in a mechanism that guarantees you can copy another object. So assuming it has a copy constructor, we go ahead and make the copy. Right. Now remember that. Oh yeah, question. No, so a shallow copy would be writing something like this Y equals, sorry, shallow copy, new, no, so there is no there is no guaranteed mechanism to shallow copy either. No, how would you do it? No, you can't even do it that way. No, so as far as I know, there's no way to do it. That's a good question, though. That might be worth looking up, see if you can actually do it, if there's some clever way to do it. As far as I know, there is not. Right. Okay. So remember what a couple of lectures ago we were talking about preconditions and class invariance. Right. So if this constructor has a precondition on that y object, right? So imagine in the projectile class you decided that your projectile never has a negative coordinate, right? You have to make sure that the preconditions are true, right? So in Java, you check or validate the incoming object, right? So after you make your copy, this is where you do your validation, right? You don't validate first and then copy, right? So you should remember copy first, then validate. The reason that you copy first, then validate is related to threading, if you know what threading is. If you don't know what threading is, don't worry about it, right? Try to remember to copy first, then validate. Right? If you take do you take an operating systems course at any point? Yes, no? Okay, so you might not ever come across this threading issue. Once you've made your copy, you've checked it to make sure it's valid, you can go ahead now and assign your field y to the copy. Okay, so that's actually a deep copy, right? So it actually makes a copy of that incoming object y. Right. Why is it required? Because you have to have the X object needs exclusive access to its y, right? If you just write this y equals y, you've got a problem, right? Your y object is now the same y object as the caller has, right? Which means your X object no longer has exclusive access to its field y, right? Anybody who has, or anybody who called the constructor can now change the state of this .y, right? Using the reference that they passed in. Right. When this happens, this is called a privacy leak. Yeah, within a second. Right. So it's called a privacy leak because something that was supposed to be private and was supposed to have exclusive access, that's no longer true. Right. Someone else can now see the private field, right, and access or modify its state. Yeah, question. So the answer is, some classes have class invariance, right? They guarantee something about the state of the object, right? If your state is represented by an object and you're not using composition, you can't actually guarantee the invariant. Right? Oop. Copy constructor. So the copy constructor is another place where you can leak a reference to an internal object. Right. So if you have a copy constructor, right, you need to make before you assign a value to this .y, you need to make a copy and assign the copy to this .y, right? So assuming your class X has a method called getY, right? You can just you get the Y object, right? And then make a copy of it. Okay. So here we're using, again, the copy constructor to make a copy of the incoming Y, right? I guess you could just write other .y here. That would be fine too. In this case, you don't have to validate the other Y object that's coming in, right? You're copying an existing X object, assuming the class X is implemented correctly. The state of Y should be fine, right? It should be valid. So you never have to actually validate this in the copy constructor. Right, so there's your defensive copy right there. Okay. If you don't do that, right, if you write this Y equals other Y, right, you're saying that your Y object is the exact same object as the other X object's Y object. Right. So again, you no longer have the X object no longer has exclusive access to its own Y. Right. Some other X object also has access to that Y object. Right. And vice versa. Right. So this is a double problem. Right. Your new X object has access to an existing object's Y object. Right. The existing object has access to the newly created object Y field. Right. In this case, every X object created with the copy constructor ends up sharing its Y object. Right, which is right. So if one X object modifies its Y, all X objects end up with the modified Y object. Again, that's a privacy leak, right? someone else has access to one of your private fields that and that they should not have access to. Okay, so in the copy constructor for projectile, if you wanted to change this to a composition, right, you would write this position equals new, point to other dot position, right? And you would write this velocity equals new vector to other dot velocity. Right, so copy, make a new point to and a new vector to object to represent the position and velocity of this projectile. Okay, you have an accessor, so you have something that that returns the state of your Y object, right? You can't return the Y object directly, you have to return a copy. So there's your copy again, right? Why is the copy needed? Because if you just write that, right, what did you just do? You just handed out a reference to your Y object, right? So in this case, it's really obvious, right? You're returning a reference to your Y object, right? In a composition, you can't afford to do that. Right. Somebody else, anyone who calls the method can now change the state of that Y object. Right. So again, another privacy leak. Right. And finally, if you have a, oops, sorry. So for get position and get velocity, right, you're not going to return this dot position, right? You're going to return new point to this dot position, right? And for get velocity, you're not going to return this dot velocity. You're going to return new vector to this velocity. Right, so make a copy of the field, then return the copy. And finally, so if you have a mutator method, so a method that tries to set the Y object, right? That's essentially the same as the constructor that also sets the Y object. Right? You have to copy the incoming Y object, validate it if you have to, right? And then assign this dot Y to be equal to the copy. Right, so it's exactly the same as with the constructor. You don't do that, so if you just write this Y equals Y, right, and again, this should be obvious that this is a problem, right? You are setting your Y object to be the exact same object as the incoming Y object, right? Whoever called the method can now change this dot Y, or the state can change the state of this dot Y, right? So again, there's another privacy leak right there. So in projectile, if you're going to implement set position, right, you would write as a composition, right, you would write this position equals new point to position, right? For velocity, set velocity, you would write this velocity equals new vector to velocity. Okay, now there's these copies happening all over the place, right? So there is a price associated with this, right? Every time you copy an object, it takes time and memory. Right. If the copy isn't being used for anything, right, or its lifetime is very short, right, then the virtual machine has to get rid of that object at some point, right? So it needs to remove the copies from memory. So that's called garbage collection. That also takes time. Right? So that bouncing ball program, that changes the position of the ball every 25 milliseconds. So here's the actual, oops, sorry. There's the actual bouncing ball program. It's in the source code for the class if you want to look at it. If you run it, right, the ball does appear to bounce around the screen. Right. I've done some surgery on the class and the point 2 class. So in the point 2 class, I'm keeping track of how many point 2 objects have been created over time. Right. Sorry, just how many point 2 objects have been created. Right. And in that bouncing ball program, I'm printing out the number of point 2 objects that have been created by that program. Right. So you can see here, it's only been running a few seconds, but it's already at 10,000 points. There's only one point that you need in this program, right? It's just the position of that ball. Right. But as the program keeps on running, right, more and more points are being created every time. Right. The points are being created because the program calls get position on the projectile to get its position so that it can draw it on the screen. Right. So every time it calls get position, a new point is being made. Right. And you see here that you end up with an absurd number of points being created when only one is actually ever needed. Right. So there is a cost to this. Right. you have to pay the price of making these copies. So you're paying a price in both time and memory. Okay, so to answer your question, why do you need this? Right, it's because not many. Sometimes you'll implement a class that wants to have an invariant. Right, so remember, an invariant is some property of the state of the object that is always true. Right, your constructors and your public methods have to make sure that the invariants are true after they're done running. Right. So for example, if you wanted to implement a class that represents a period of time, right? So for example, something that represents a meeting in Teams or something like that, right? Where there's a start time and an end time, right? That class has an invariant, right? Every period of time has a start time and end time where the end time always comes after the start time, right? So there's your class invariant right there. All right, so when you go to implement this class, I guess you need a way to implement to represent the time. So there's a class called date in Java. So it's in Java util that is able to represent a time. Right? It's called date, but it actually represents a time. That class is actually deprecated. So it's recommended you no longer use that class, but we're going to use this in this example. Right? Date is mutable. Right? So you can, given a date object, you can change what time it represents. Right? So we have this class invariant. I'm going to use a date object to represent the start time. I'm going to use a date object to represent the end time. In order to ensure that the invariant is maintained, we have to use a composition. Right? If I hand out a reference to that start time, someone can change the start time so that it's now after the end time. Right? If I hand out a reference to the end time, someone can change that reference. Someone can change that date object so that it becomes before the start time. So here we have to use a composition, or you have to do something to make sure that you never return the or give access to the start and end time. Right? So in a composition, the whole object gets a solid diamond beside it. Right? So the solid diamond indicates composition. This says that a period object is a composition of two date objects. Composition, like aggregation, is a one-way relationship. Right? A date cannot be made up of a period object. Okay, so date is funny. So it's one of these classes that doesn't have a copy constructor. Right? If you're going to implement a composition, though, you need to be able to copy a date. So the way you do it is you call you call this method called getTime, and you can pass that value to the date constructor, and that will end up copying or making a copy, making a new date object that has the same time as D. Right? GetTime returns a long value. I think it's the number of seconds since January 1st, 1970. You might ask why that's the case, because it turns out that's the standard way that time is represented in Unix-like systems. So something like Linux or Unix, including your Mac, the default representation of time is the number of seconds since January 1, 1970. I forget which time zone. Anyway, so here's our period class, right? It's got a field called start and a field called end, right? The start time and end time. They're private, right? They have to be private in a composition. If they're not private, some other class can look into your period object and get direct access to the start and end time. Right? So it's pretty important that these are private. There's our constructor. So our constructor is going to let the caller make a period object given a start and end time. Right? And so it looks like the caller is doing the right, whoever implemented period is doing the right thing. Right? They're going to make sure that the start time comes before the end time. Right? So they compare start and end, right? Using compare to. So date has a compare to method because it implements the comparable interface. Right? So if the start time is greater than the end time, right? So if it's greater than 0, it throws an exception. Right? So they actually, whoever implemented this did actually try to ensure that the invariant will be true. Right? Unfortunately, they then wrote this start equals start and this end equals end. Right? So the internal start object is the same object as the one that was passed in. Right? The internal end object is the same end object as the one that was passed in. Okay, so as soon as you write that, right, as soon as you write that constructor, your class is dead, right? It's busted. So here, someone makes a start and an end time, right? That's 10,000. So 10,000 here is 10 seconds, right? So this is the number of milliseconds. So someone's making a new date object equal to the start time plus 10 seconds, right? So the end time really is after the start time. They call the constructor, so the constructor tries to validate start and end, and this validation is successful, right? The problem is that the caller can now modify one of these two things, right? And the period object, its invariant is now broken, right? So what do these do? So end set time to end get time. So this doesn't change. So set time is the method that changes the time that's represented by the object, right? Get time represents the current represents the time represented by the object. Right. So option A doesn't do anything, right? It changes. It doesn't actually change the end time, right? Or it sets the end time so that it's equal to the end time. Right. The next one changes the end time so that it's equal to the current end time plus 10 seconds, right? So it moves the end time into the future, right? So that doesn't cause any problems. This one changes the start time so that it's equal to the end time minus 1 second, right? That means the start time is still 1 second ahead of the end time, so that doesn't cause any problems, right? This one sets the end time so that it's equal to the start time. Oh, I just realized something that is wrong. Greater than or equal to. So the start time is supposed to be strictly before. This sets the end time and start time so that they are the same time now, right? And so that causes a problem, right? Your invariant, which says the start time is always before the end time, is no longer true, right? Even though you never actually did anything to the period object, right? You never asked the period object to change its start or end time. You simply adjusted one of these two variables here, right? And that breaks your period class now, right? It has an invariant that it can no longer ensure, right? So to fix that, the way you do it is, remember, copy first, then validate, right? So copy the incoming start time, right there. Right. Copy the incoming end time, so that's right there. Do your validation the correct way, so greater than or equal to, right? Once you've done your validation, go ahead and assign your start and end fields to the copies. There's the copy constructor, right? Implemented exactly the way you were not supposed to if you're implementing a composition, right? So this copy constructor says that the newly created period object has the exact same start and end time objects as the existing period object, right? So they're the exact same objects. What does that mean? It means two period objects are now sharing the same start and end time. Right? If one changes its start time or end time, the other object also has its start time or end time changed. Right? Now this one doesn't break the invariant, but it does cause an issue, right? If you copy a period object and change its start and end time, then the copied object also has its start and end time changed. It's probably not what you want, right? So the solution here, again, make a copy of the incoming start and end times, right? The accessor method. So imagine you have a method that returns the start time and you have a method that returns the end time, right? If you return a reference to the object, that's a problem, right? Anybody who calls get start can use the return value to change the start time to whatever they want, right? They can now change the start time so that it comes after the end time, and now your period invariant is broken, right? So again, privacy leak, privacy leak. How do you fix it? Return a copy. Right. Finally, set start. This is the same as the constructor, right? Set start changes, right? Changes the start time to the new incoming time, right? What do? You validate the new incoming time to make sure it's still before the end time? If it is, go ahead. If it is, you should set this start to be equal to a copy of new start, right? If you write this start equals new start, again, you've got a problem, right? Whoever passed in that variable there, or that that reference there, right, can now change the start time of that period object. Right. So copy first, right? Then validate, and then go ahead and assign the field to the copy. Oh, sorry. Okay, so in all of these cases here, right, if you have a constructor that takes in a Y object, right, you have a constructor that copies another X object, you have an accessor method that returns the Y object, and you have a mutator method that sets the Y object. In all of those cases, you have to make sure that there's no privacy leak, right? If you ever find yourself writing something like this Y equals Y or return this Y, right, that's a problem, right? Those are all examples of privacy leaks in a composition, right? In an aggregation, it's just business as usual, right? But in a composition, these all cause the composition to break. Right. If you implement a composition, right, and you have a privacy leak, that allows some other object to control the state of the object of the leaked field, right? Whoever gets a reference to that object can cause the state of that object to become inconsistent, right? So, for example, if you had a credit card class that handed out a reference to its internal expiry date, right? Someone can change the expiry date so that it becomes before the issue date, for example, right? Or they can make your credit card never expire or something like that. Right. If you're implementing a composition and so when you're implementing a composition, you're doing it because you're trying to ensure some sort of invariant is true, right? If you leak one of your internal fields, that guarantee goes away. And so your class no longer has any real invariance. Right. So, for example, if the period class exposes a reference to one of its date objects, right, whoever gets that reference can change that time so that the period class, its start time no longer is before the end time. Right. And finally, you no longer have a true composition, right, because you no longer own your own field. Right. The consequence of this in Java is that if you hand out a reference to one of your internal fields, right, and your object goes away, so you no longer need it, right? Whoever has a reference to that internal field, that internal object can't go away until the reference to that internal field also goes away, right? So what that means is that an object that dies, right, so is no longer needed, and its memory and resources are supposed to be deallocated, its parts might not die with it. So its internal objects, the memory associated with them may not be deallocated. And so that can also be a problem. Right. If you ever need to make an immutable object, like string, right, you have to make sure it's a composition. Right. So to make an immutable object, right, point number one is kind of obvious, right? Your object should be immutable, so don't give anyone a method that can change the state of the object. Right. Number two, we can't talk about yet. We'll be able to talk about that after reading week. Right. But number five, prevent clients from obtaining a reference to any mutable fields, right? That's essentially saying you have to implement a composition, right? Because if you do hand out a reference to one of your internal fields, right, and that field happens to be mutable, right, whoever got a reference to that field can now change the state of that field, and your immutable object is no longer immutable. Okay, so I guess that's a good place to stop. So the next part of this is going to be, so what happens if you implement a composition, but the field that you're composing isn't just a plain old object, but it's something that has or can contain one or more objects. So what happens when you implement a composition with an array or list? Right, exactly what goes on in Java. So I guess I'll explain that after reading week. And so we're done for today.